this quiz was a forced review. Forced review of lecture 3. All right, let's continue with lecture 4, and this is what I call 4.2 errors. So last time we went over a number of ways how you actually are supposed to structure your code so you put in less errors while simply typing the code up. Okay? So there is a number of errors you put in, and I'm going to refer to them as unavoidable errors. Okay? You didn't have coffee that morning, or maybe you did and you're maybe overhyped because you had too much coffee. You have some other things on your mind. No matter what, humans are going to type in errors. And some are going to type in more than the others. But regardless, those people who are successful at catching errors are simply those who are alert and aware that they're going to be putting in errors and they're just dealing with that. Okay, we're not perfect, so we're always on a quest to improve. So essentially, that's what I refer to as debugging. Okay, debugging your code is removing errors that are there simply because you were a little sloppy or not. Maybe you didn't know something, so as you go, you actually have to go and improve. Now there is a number of errors that we simply cannot avoid, and that those are the topic of our 1 or 2 next classes. Unavoidable errors in computing. Have I posted this? I forgot now. Is lecture 4.2? I thought I did. Okay. Or is it 4.1 only?
4.2.
Yeah, it's 4.2 on there. Okay, good. So basically, unavoidable, there's these bugs, and we refer to them as bugs that are avoidable. They're simply could be there because essentially people put them in. But there are certain errors that are unavoidable, and typically it's a round of error. So we have numbers in math that have infinite number of decimal points, or numbers beyond the point. But we cannot store all of those numbers. Okay? Infinity is not something we can store on a computer. So basically, because of the mismatch in how much space I have and how much I can actually store, I have so-called round-off errors. Often, I can actually store numbers individually. But once I'm actually trying to add them up, they're so far apart that in the process of trying to add them up, I'm going to lose some accuracy. So that's, for instance, the case here. We will actually see that. So if I have, for instance, there's 10 to the 3 here and 10 to the minus 10 or so, okay? And basically they're so far apart that once I put them together, I cannot store them effectively. And we will actually go through reasons why is that so. And then I also have truncation error. So this is just the physical space that I have to store one number, okay? And I will make those mistakes. And then these will propagate. So once you start computing, and you will see once we actually start putting together algorithms, in order to get accurate or close to a solution, I will have to repeat certain loops 1,000 times. So at every point in that iteration, you're going to actually introduce a small error, because at every point of that for loop, you're actually going to have to chop off a part of a number, right? And those can pile up. And it's okay as long as that pile up is limited. Okay? So we actually have to figure out the ways that we put the control on error. And then there's truncation error that is simply there again if I have infinite sum. Okay? This is the basically error of chopping off the last part of the sum, so I can actually just figure out first 10,000 or first 100,000 or whatever it is, but first finite numbers. So that's basically when I have a mathematical formula, and that mathematical formula I represent by a truncated version of it. Okay, so that is truncation error. Yes?
So in MATLAB though, you can only do like a long form basically. It has like 15 decimal places. So why would you go to like 10,000? You know?
So that's a good point. So he's essentially saying, if I go to 10,000 here, and then I attempt to store this number. While storing the number, I'm going to have a round of error. Okay, so whatever result I get here, I'm not going to be able to store accurately. So yes, you're going to have errors on top of errors. Okay? So that's a great question. So most likely you're not gaining nothing by going to 10,000 here, and 1,000 or even a 500 is more than enough. Okay, so those are certain things that you actually have to find out, and they're formula by formula dependent. Okay, in some cases. But yes, it becomes at some point, it's like even if you can do something supposedly more accurate, there's another type of error that could bite you at the same time. And that's something that we have to live with for the most part. Okay? I can live with a certain number of errors. So let's say that I'm driving to San Antonio. For all intents and purposes, he's driving to San Antonio often. So for most intents and purposes, you need to know how long is it going to take you so you can have enough gas in your tank, right? Then your estimate of distance, plus minus 0.1 mile, doesn't matter. Okay. Whether you say, oh, it's how many miles?
75 miles.
75 or 75.1 or 75.2, irrelevant. For all intents and purposes, you need to know that it's roughly 75 miles, and that you need to get a tank of gas, and you're good, okay? So, for a lot of applications, yes, you're losing accuracy, but it might not matter, okay? Now, if you go into a lab, and that's actually something that's biting us here often, so most often if you do your flow experiment in a Berea sandstone, you have to be able to inject and measure a number of milliliters of either oil and gas or whatever fluid you're using. Okay? Now we want to actually study shales. Shales have 1,000 times smaller pore spaces. So suddenly the volumes you need to inject are also 1,000 times smaller, but take about 1 million times longer. So basically, now ability to accurately measure nanoliters is important. And whether you have a nanoliter leak is important. And your nanoliter leak did not matter as much when you were injecting milliliters. So things are relative, and it is actually your task of as an engineer, so that's why you need to know a lot of physics at the same time as knowing how the computation works, to actually figure out does it matter. Okay. So basically you have to be aware of all of the errors that could be there, but also you need to actually gauge what is the most important one to look after. Alright, so we have digital representation of numbers in computers, and we have fixed number of digits that represent the number. Okay. So one thing that we actually have to go back to is now the original way, how does computer actually store numbers? And most of you have heard of zeros and ones, right? When we refer to computers, we refer to zeros and ones. So typically, 1 bit is referred to as a 0, 1, and that's basically on or off, okay? Light on, light off. So basically that's very easy for computer to figure out what is 0, what is 1. And then we organize those bits into groups. One word is 8 bits, and it is called 1 byte. So our essential unit of storage in a computer is 1 byte. Now, so this, basically that's the smallest sort of single unit that I can take to store something, is 1 byte. I cannot store, if I want to store only 2 bits, okay, out of that 1 byte, out of 8, I still have to waste 1 byte. That's my little measure that I can store. So I cannot store less than 1 byte, okay? So now, dependent on the size of the numbers I want to store, I can use actually 1 byte to store one number, but then I'm really limited in the size of the numbers I can store. Or I can use 2 bytes, 4 bytes, 8 bytes. Okay. So essentially, you heard about 8-bit, 16-bit, 32-bit phrases, right? And those are actually the number of bytes or number of bits that I'm using to actually store a number. So different numbers take different type of storage and different number of bytes that I use to store. So in MATLAB, most often, we were defining variables, okay? And often we were just saying A is equal to 2, C is equal to 7.2, and we were just like typing in numbers and we really weren't thinking about it. That's because MATLAB has a general policy of storing all numbers, unless you specifically ask otherwise. All numbers are stored as real numbers to the maximum capacity. That's called double precision. And then all of the operations that are done with those numbers. So there's no, so often that could be based on resources for certain problems, but that makes things easy in terms of you don't have to think of declaring which number you want to store. If you go to a different or study a different programming language, in a lot of them you have to declare what you want to store before you actually store it. Okay? And then of course there could be some errors if you attempt to store an integer into a double precision real number or a double precision real number into an integer. Computer might be kind enough to store it anyway, but it might be actually creating a bug. So it might actually produce a junk number as a result of the entire operation. So it's quite literally trying to store something of this shape into this. It's not going to work, right? So you have to actually be aware of the shape if you are learning different programming language. So this is just a hint for you that if you, in your career, if you start learning a different language, you might be have to be aware of that. Okay, so let's actually now look into some numbers. So here's an exercise that is going to lead us to how we actually represent integers in terms of these bits, 0 and 1. So let's say that you have only coins of 1 cent and 10 cents. Okay. What is the least number of coins of each kind that you need to actually have 25 cents in your hand? How many of 10 cents? 2, and then 5 of 1 cent. I could have just 25 of 1 cent, right? Or I could have 15 of 1 cent and 1 of 10 cents, but that's not the least number of coins altogether. Yes? Now, so 25, basically 2 of 10 cents. So basically the algorithm here is I take the largest type of coin that I have and see what is the maximum number of those that I can fit into the number I'm trying to represent. Okay? And in this case, that's 20 cents out of 25. That's 2 of those coins, and then 5 of the smaller ones. So that is actually precisely how we represent numbers and how we are used to representing numbers in what we call base 10. Okay? So our numbers, they increment based on number 10. They don't increment based on a dozen, which is one of the old units. Okay? So basically, after this, I have ones, tens, hundreds, thousands, and so forth. Everything is based on number 10. Now, just like we're working with 10, we could work with 2. Okay? So imagine that you have coins in terms of 1, 2, 4, 8, and 16 cents. And answer the same question. What is the least number of coins of these that you need to represent 25? So how many of 16? 1. What's left once I take 16 out? 25 minus 16 is 9. Then what's the largest one I can fit into 9? 8. And then 1. Okay, so those are the 3 coins. Okay? So this is actually, so now imagine, just like we had base 10, this was 2 times 10 plus 5 times 1. So 25 in base 10 is 16 plus 8 plus 1, which is 1 times 16, which is a power of 2, right? plus 0 times 8 plus 0 times 4 plus, no, 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Okay? So this is my representation in base 2. Okay? And those are my ones and zeros that I actually store on computer because that's what computer knows. Okay? Computers cannot have 10 different digits. It has only 2 digits, on or off. Okay? So these are now my bits. Okay? So this is basically corresponding to 1, which is 10 to the 2 to the 0, just like I had 10 to the 0. Okay? Then 0 times 2 to the 1. Then 0 times 2 to the 2. Then 1 times 2 to the 3. 1 times 2 to the 4. And actually then I have your 0 times 2 to the 5. And 0 times 2 to the 6 to put it all into 1 byte of memory. Okay? That's what's done in computers. Okay? So this is how computer will actually represent number 25. Okay? So again, base 10 is a choice. And it's a choice because humans have 10 fingers. That's why 10 base 10 is natural to us. Okay? But number 2 is not so natural to us, but it's natural to a computer which has on and off switch. It doesn't have 10 fingers. Okay? So basically in order to represent, to fit numbers, we have to convert them to base 2 and then work with that. Yes?
So like say you have to do like 2 times 16, will the computer store the number in the same way or will it store it differently?
You will never do 2 times 16 in base 2. Then you can actually fit one more, then you can fit 32. 32 is the next power of 2. Okay? So if I have base 2, my digits are 0 and 1. If I have base 3, what are my digits? They're 1 and 2. Okay? If I have base 7, what are my digits? Right. So it's always 1 less because otherwise I can fit in the next power up. Yes.
I have a conceptual question about like why I only store zeros and ones. Is it because of like polarity or like a positive and a negative, like actually like inside the drive itself?
Yeah, you have on and off.
Yeah.
You also,
Is that positive and negative though? Like as far as like electronics?
quite frankly, I don't have a precise answer onto what is precisely on what is, but it's current on, current off. Now, how is that resolved locally? I don't know, and you know what also? Technology changes, so those things change. So as I'm improving, but that's actually, how about you research that and get back to class? What does basically, what goes on a chip? Well, that's an interesting question, right? What goes on a chip? And we do know that like we can store things into smaller and smaller things. Our phones went from quite bulky to quite something slick. Now they're actually back to bulky again because we want these screens on there. But essentially, well, yeah. But essentially, you can make them smaller, but humans also still have to read on that phone, right? So basically, as technology increases, I don't know what actually goes into making those chips and storing all of these. So how about you look into that? What is the hardware part of this?
I think it's like really big. I guess if it's like an old chip, I would think it would be.
Well, old chips were those vacuum tubes and whatnot. So yeah, so do you remember at the very beginning of the class I showed how big computers were?
Yeah.
They were fitting into a room. That's why.
Passengers for that.
Alright. So basically you can see how actually if I only have 1 byte, which is 8 bits to represent the number, what are all of the powers of 2 I can fit in there? What's my largest number? If I have 8 bits. So maybe, yeah, so basically my largest number is if I put all ones, right? So if if I put all ones here and add more, 3 more, okay? It's gonna be 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. That's my largest number, whatever that comes out. Yes? So, is everybody following?
Not 128.
Yes, you have 255 as the largest number. Okay. So some of those is actually 255. So if I put all ones into 8 bits, and that's the largest number. So basically between 0 and 255, but of course I'd like numbers that are larger than 255. So for that, I can actually either use 16 bits, so I can have 16 bits and keep going, okay? And that largest of those numbers is around 32,000. I'm going to give you a formula how to compute quickly without adding them all up in a second.
8 bits means 2 to the 8.
No, 2 to the 7. You start with 0. So 2 to the 0, 2 to the 1, 2 to the 3, all the way to 7. Okay? So just a quick digression, the way you quickly compute this is when you have something like 1 plus x squared plus all the way to x to the n. The formula is x to n plus 1. This is the same as this. So if I had 1 plus 2 plus all the way 2 to the 7, that's 2 to the 8 minus 1 divided by 2 to the 2 minus 1. And that's actually 255. That's just a mathematical formula. You can actually check it easily. Okay. So it comes in handy. So if I had 16 bits, okay, this would actually go to the 2 to the 15. So the largest number is 2 to the 16 minus 1 divided by 2 minus 1. So that still might not be enough, okay? So in that case, we might actually go to 32 or 40 or even 64-bit word.
Why do you need all those numbers? Like, you have different
Numbers.
or different.
Yeah. I mean,
basically.
yeah, what if you want, in your reservoir, you want information on every 1 foot? And your reservoir is definitely more than 255 feet deep. Okay. Even 32,000, we're pushing it to 32,000 feet. Okay, in terms of the total limit, especially if you have vertical and horizontal sections.
You can't add the bytes together.
Well, I'm not going to probably use integers, I'm going to probably use real numbers, but you can come up with applications why you need numbers that are larger than 32,000. Okay. Alright, so here's another example. If I had number 173, again, I try to fit the largest power of 2 I can, okay, and that's 128. Okay. Then what's left, I try to what's 173 minus 128. You have MATLAB open, for goodness sake. Come on. Alright. If not, if you have. Okay, so then in 45, I have 32 as the next largest power of 2. Okay. And then 8, and then 4, and then 1. And that's basically 2 to the 7, 2 to the 5, 2 to the 3, 2 to the 2, 2 to the 0. So corresponding numbers are 1 here. Okay? So this is 0 power, first, second, third, fourth, fifth, sixth, seventh. Question?
So I know you said it before, but it can only go to the power of 7 if it's 8-bit.
Yes. Yes. Okay. Again, most computers reserve 16 or 32 bits for integers. So upper limit for a positive 16-bit number is 2 to the 15 all the way plus 1, which is according to this formula 2 to the 16 minus 1. So in a 16-bit number, or a 32-bit, 16-bit number, this is my largest positive number I can store. Now, if I actually want to store negative numbers, I have to come up with something different. And these are all rules that are kind of built in. Okay? So if I want to do negative numbers, then one of those bits has to be for the sign. So I have one less bit for the actual number. Okay? So basically then, this first bit, this is 16 of them, is for the sign by convention. And the rest of them is the magnitude of the number. And those are the rules that we actually need to know. So in MATLAB, again, we're avoiding it by actually using the same double precision real number for everything. But if you wanted to tell computer, if you didn't want to waste memory and you wanted to tell computer what to do, then you would actually have to, this is so-called signed short integer that it has 16 bits, and signed means that one of the bits is reserved for sign. So let's say that I have this 25 that we came up with, okay? And let's say that it's actually stored in a 16-bit signed integer. Write down on a piece of paper or wherever it is that you're writing notes, write how would this number look like. So sign will be 0 for a positive and 1 for negative. So what is a positive 25 going to look like in memory? And what is the negative 25 going to look like in the same memory for this 16-bit representation?
So there are actually 17 digits right there.
Did I put 17? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, their total was 16.
In the magnitude, right?
No, in everything. In everything. Great question. First bit, okay? First bit is the sign. The other 15 are magnitude if you have a 16-bit.
Is it left or right?
Great question. Different hardware, different. There's a called big endian and small endian, and yes, that can wreak havoc if you don't know which machine is which. So some machines go from left to right, some machines go from right to left, and you have to know. And yours truly went through a lot of pain once upon a time as a graduate student, not knowing that fact. Essentially, so basically when I'm storing arrays, a lot of files, doc, PDF, TIFF, JPEG, they are format files. So the beginning header of the file actually has all of the rules stored. So your computer encounters a JPEG or your phone encounters a JPEG and knows precisely what to do because those are built-in formats that are up to standard. You could actually just store an array and only you know what you stored. Okay? And you stored it on a machine that, for instance, does left to right. And you try to transfer it as a file to a machine that does the other way. What you're reading is garbage, unless you know precisely how to read and flip. Luckily, there's finite number of combinations that you can do to actually figure out this.
Highest value, right? 25%. I can just figure out the low, like,
Just to answer the question, this one. So basically, you will have here 10011. That's this 5, right? The rest will be zeros, and the lead will be 0 for a positive 25, and the lead will be 1 for a negative 25. So that's how 25 will be stored. But you have to have a custom who is first, who is last. Okay? All right.